So this video is a part of a presentation on denial of service on RTC systems. This is the second part, which is about DoS on signaling. When it comes to signaling DoS attacks, the most well-known attack probably is SIP flooding. This consists of sending SIP messages repeatedly, possibly at high rates. We'll be talking about two SIP methods that are often used in SIP flood attacks: invite flood attacks and register flood attacks, or attacks using authentication attempts. But first, one has to ask, why is it so effective? One reason, and it's not to be underestimated, is that SIP parsing can be CPU intensive. With register flooding, when authentication is taking place, it might be that database lookups are resource intensive. You might have a database lookup for each authentication attempt, which becomes a bottleneck during an attack. We have seen cases where the system runs out of memory for storing the AOR or needs to look up the AOR, both of which may be bottlenecks during certain SIP flooding attacks. And then there is the custom stuff, which might trigger authentication whenever authentication takes place or whenever authentication fails. Things like logging and notifying other systems may also lead to denial of service and can be triggered through a register flood. When it comes to invite flood, things get a bit worse because we have the same issues that we have seen with the register flooding and more. For example, if the target system opens UDP ports to handle the RTP stream, perhaps for proxying RTP, then during an invite flood, the target system might run out of ports. Additionally, each dialog needs to allocate resources such as memory to keep the call state, which also takes more resources than other SIP methods. And of course, there is a lot of custom stuff that may be built on top of call handling, such as voicemail or call recording that may topple over and not perform well when the system is under an invite flood attack. So now we have to get to our SIP flood demo. Our beautiful piece of art here that represents our network diagram shows the internet in the middle. On the right-hand side, we have the target machine that we describe in the introduction. And then we have on the lower left, we have Zoiper and Linphone behind a router that are used to make calls through the target. This is done to be able to test the system and see if calls can be still done before, during, and after the attack. Finally, we have three attacker nodes, each with minimal specs, also connected to the internet that will attack the target using SIP register flood in SIPVicious Pro. Full disclosure, we did make some minor changes to Asterisk pjsip and Kamailio configuration by, for example, increasing the thread pool size and forcing Kamailio to use 8 children. This should only improve the performance of the target system. We start with a demo of SIP flood register. So we have 5 windows. The top one is where we SSH to the target machine. On the bottom left, we run Linphone, and the rest are SSH'd into the attacker machines. Okay, so first we SSH'd to the target machine, and then we start Kamailio after starting RTP proxy, and we load up htop. We can see that Kamailio is running and also MySQL or MySQL. Next, we zoom in to the local window, which shows the contents of a bash script that we will be running. It runs linphone, essentially. It does auto answer, registers to the target machine, to the Kamailio, and whenever a call comes in, plays an audio file. So we can start that. And we can hide that now. Next, we start Zoiper. Now, Zoiper, and we can call linphone over the target, proxying the RTP, and we can see that the call goes through. Now we can start the attack, subvicious DoS flood tool on each attacker node using the register method and the fake authentication method, each having 5 connections. The fake authentication method tries to authenticate a lot of times with fake usernames and passwords. And then we try to make a call again. We can see that the signaling actually worked at first because we can hear the ringtone, which means that a 180 try message was received. However, the call does not get picked up by linphone because the system is already struggling. The second time that we try this, signaling is not responding in a timely fashion, and it will simply time out. If we were to look at htop, you can see that the MySQL daemon is using a lot of CPU resources, and Kamailio is also high on CPU, but it's mainly the MySQL server. Okay, so we can stop the attack, and you can see that the system actually recovers pretty quickly. The call goes through very quickly then. So next up, we have a presentation with a demo with Asterisk with pjsip. Again, we SSH to the target system. Start screen and Asterisk within screen, and then htop, and notice that Asterisk is running. Then we switch to the Asterisk console. We can see that there is already some attack going on from someone else. This is not part of the demo, it's just internet background noise.
I am sorry, but
Then
that's
we
not a
make a
valid
call
extension.
using Zoiper
Please try
to an
again.
invalid extension, and we see that the voice of Asterisk can be heard. So now we can start the actual attack. It's the same exact attack that we saw before from 3 different attack machines. I quit the Asterisk console just in case the flood has any impact on the system, and instead switch to watching htop. So you can see that the processes are taking a lot of CPU. So we run another test with Zoiper
I am
and
sorry,
see that
but
the
that's
call
not
is
a valid
actually still going
extension.
through.
Please try again.
We do another call, but this time it takes a while to go through.
I am sorry, but that's not a valid extension. Please.
At this point, we try again, but this time Zyper will time out. So now we'll start one final call and stop the attack. So we'll start the call and go to the attacker machines and stop the attack.
I am sorry, but that's
And we
not a
can
valid
see
extension.
that
Please try
the
again.
system recovers pretty quickly and the call does go through. Next, we have the same demo on Asterisk as well, but using ChanSIP this time instead of pjsip. So we're already SSH'd to the machine, to the target machine. We can test using Zyper to
I
make sure
am
that
sorry,
calls
but
can be
that's
made.
not a valid extension. Please try again.
Then we switch to the attacker machines and start the same attack on each node. We switch to HTOP to monitor the system for high CPU. And we can see that Asterisk is topping one of the vCPUs. Um, but if we switch back to the Asterisk console, we can see some stack traces. So now we try to make a call. And the call simply doesn't go through. So signaling can often happen on top of TCP or TLS. One issue that we noticed is that a number of servers might not handle huge numbers of connections. So we developed a tool that can send a large number of SYN packets and then responds to the SYN acknowledge response with push packets, thus keeping the connections open. This results in a SYN-ACK flood and causes a number of servers to run out of file descriptors. If they are vulnerable, they will not be able to handle new connections. Something else, but related to TCP and TLS connections, that we noticed while testing Asterisk was that whenever an attacker sends a SIP message and disconnects, and then does this repeatedly, the Asterisk server would crash. This was reported to the Asterisk team and was fixed sometime last year. We have also tested SIP with TLS Client Certificate Authentication instead of just digest authentication. In this case, we found that by attempting to authenticate with a certificate containing a large number of fully qualified domain names, FQDNs, and doing that repeatedly, this would flood the authentication server. the target system that we were testing, would look for a particular FQDN and was not expecting that each certificate would have more than one. So it choked on that. Now, something quite different, but specific to WebRTC. So we were testing a WebRTC system that made use of a proprietary protocol for the signaling on top of WebSockets, which looked similar to the following message. So you have the first JSON message, which is the header describing the second message. Essentially, the header specifies the length of the body and the type of the body. So we saw that to attack this, what we did was we wrote a Python script which replaced this message that we just saw, and each time mutates the message using Radamsa, which is a fuzzer, which is a mutator, before sending the message. Therefore, each message could be slightly malformed, but still possibly a valid message. We noticed that one particular message that was produced by our tool was generating a 500 error response, and all WebSocket connections were getting disconnected as well. Not just ours, but also connections from other clients. So then what we did was to simply take that message, which looked like the above. The length, you might notice the length is a number that caused this problem. And we replayed this message consistently. This caused the signaling system to simply become unavailable for legitimate clients. So that's it on signaling. Please check out the next video, which is about attacking the media.